The magnetic field, the magnitude is equal to the ratio of maximum force acting, and these units of the magnetic field are Tesla. Well, you know the car, Tesla? Yeah. So that's what I was discussing with some colleagues. They say, oh, Tesla, this is a must for young people. Yeah, probably yes. Yeah, that's a good car. It's very nice to drive it. Yeah, Tesla, this is the name of a Serbo-American scientist who was working with the magnetic phenomena. Yeah, and you can see that this is newtons divided by AN, because one N is a cancellation in the denominator and the denominator. And just the typical values. Well, magnetic field, it's a source of Earth, it's a source of magnetic field. Earth produces magnetic field like a magnetic material. Yeah, so, and if you will measure, well, with this kind, you will find that it's like a 10 to the minus Tesla. Some of you will be doing the laboratory work, and you will measure the magnetic field of B. If you are speaking about Tesla, so this is magnetic resonance imaging system that I used in medicine. So this is typically magnetic field values. Yeah, and well, this is a few years already resulted, like 70 Teslas. This is something a maximum produced magnetic field. But probably, if you will look for these values today, you can find a bit high value, because usually this kind of magnetic field, they are produced using superconductors. You remember we spoke about this material. Yeah. So, well, we know already that magnetic field lines, they can be visualized using this small arrows, magnetic arrows, and the property of the magnetic field lines that they are closed. They are closed. You remember, for the electrostatic field, they started at positive and ended at negative charges, and these lines are closed. They never end, and you see this is inside of the material lines are getting in. Yeah, and if you have a few sources of magnetic field, then in this case, the same principle of superposition applies. Yeah, so the resultant B reduced by I number of these sources just should be summarized in the vector form. So certainly this is you can have some problems to solve. For example, if you have one current and another current in perpendicular direction, so it's a B and it's a B, so you can find the resultant at the point somewhere. This is just a well, just please pay attention. This kind of field, when these lines are closed, it's called solenoidal vector field. Solenoidal vector field. So this is specific name or physical description. Yeah. As you may recall, I spoke a bit about the history, and we have mentioned it. Biot Savart. This is two French scientists, Biot and Savart, who have contributed to this research, and they proposed how to calculate. We spoke how to measure, but now we can calculate the magnetic field, and for this we apply this. Just apply the superposition principle. Just let us try to understand it, how it works, and how can we do this to calculate magnetic field produced by different configuration of electric current. Well, let us realize that this is a conductor with electric current, and it's linked to a conductor, for example, and this is a DL. It's an elementary value of the length, DL. And direction coincides with the direction of electric current. And we are interested in the magnetic field as the point is defined by the position vector R. According to the Biot-Savart law, direction or dB produced by dl, so direction of this elementary magnetic field produced by this elementary lens with electric current, it will coincide with the cross product dl cross product r. What does it mean? It means that this is a vector that is perpendicular to these two, yeah? And if I will recall the properties of cross product, I will find that dB at this point is perpendicular to this plane, and we see just a tail of this vector. It's a nose, it's in this direction. Okay? Yeah, so this is a direction, it's a given, yeah, and there is some coefficient. This coefficient in SI units, it's mu 0, mu divided by 4 pi. So this constant that appears here is called permeability of free space. Permeability of free space. So this is magnetic permeability mu, for air, it's a 1, and you will see, as we will discuss the magnetic material, you will find that this mu is higher, and in this case, magnetic field inside, it's increased. It's increased due to contribution of magnetic field produced by this material itself inside. Okay? Yeah, and suddenly, if I need the magnitude of B, so this is the direction, the magnitude, probably remember, it's a sine alpha, where alpha is an angle between these two vectors. I mean that if you are far away from this point, so contribution by this dl is rather small, and if you are closer, so this contribution is a bigger one. Yeah, and the resultant d, it's integral. So according to this superposition principle, if we interested in calculation the magnitude, so we should calculate integral from here. And I will show you some examples how this it's done and how to calculate magnetic fields. Yeah, good. Yeah, and this is just a graphical presentation. Well, we spoke just about a single line of B, but certainly if you will look in the space, so you can put everywhere, let's say plane, you put the magnetic arrows, and you will find that these magnetic field lines B, they are closed and they go around this conductor, the electric current. So this is just a higher quality of presentation. You can see dl, r, and dB produced by this one, and correspondingly in this point. So you can see the influence of angles. So this, let's say, at this point it contributes it's smaller dB, at this it's higher dB. You remember the dependence on angle. Good. And now, it's you remember that magnetic field can be described in terms of two vector values. B, magnetic field or magnetic flux density B, and magnetic field strength H. Yeah, so, and it takes into account, well, as I mentioned it already, magnetic field produced by material inside. So magnetic field is outside and magnetic field is inside. They can differ, yeah, and according to the definition H, this is magnetic field intensity, it's a B divided by mu 0, where mu it's a magnetic permeability. So I mean that if we need all these expressions we wrote, they are valid for this vector dH as well, like for dB. Just as we divide by this, you see we are just missing this partition here because we have divided. Why is important this? Yeah, because you may recall we discussed about the electric field in electrostatics. And we discussed about the polarization, and we discussed about the electric displacement vector. Inside of the dielectric material, electric field is reduced, and this vector D calculated, it allows us to find the influence of free charges on the electric field. Similarly, for the magnetic field, we are using H that takes in account internal magnetic field. And B, it's an analog of E of electric field. If you look for some correspondences between these two phenomena. Certainly, this is different fields, but just to show that there are some parallels, that take into account. Yeah, some interesting, according to my point, this is a Earth's magnetic field. So, I have already gave you the typical values, like a 10 to the minus 5. Yeah, if you will look now with the needle compass needle, we will find that the North Pole, I mean geographic North Pole, it corresponds to the South Pole of magnet. Yeah, so the magnet South Pole, it's in the direction of geographic North Pole. So the next, what you will find that it doesn't coincide with this axis, but this magnetic field lines are like inclined with respect to the axis, and this axis rotates like you remember we discussed this mechanical spin when it's a precision, so it rotates like this. B is up, but it rotates all the time. So this magnetic field, well, it's like about like some conducting material inside. This is a motion of this conducting material is responsible for the production of magnetic field. And certainly there is a dependence on geographical position. So probably the most would be challenging to measure direction of magnetic field here, because magnetic field lines are perpendicular to the surface, and your arrow, it shows just a horizontal component like you were doing in the laboratory work. So one more thing probably you heard about is solar wind and magnetic storm. So what is this? It happens that in the sun, the positive particles, flux of positive particles is always escaped from the surface, and this activity of escaping, it changes regularly. Well, there is some periodicity like 20 years, so the activity of sun becomes very high. So what happens in this case? Yeah, in this case, these magnetic field lines, they are distorted by this one. Magnetic field, it protects us against these particles, but in the high flux, well, you can see that these magnetic field lines are distorted in space. So the people, they sense this, they are sensitive to this, and it's very important to know when it takes place, because you should take care, of yourself during this magnetic wind. Yeah, and now just an example how to calculate. I will not go to the details, but I just will describe the principles. Well, this is a typical problem that is can be solved analytically. Well, we have an infinite wire. We allow the electric current pass like this one. You see, this is the direction. So what we are doing? Well, we are just defining dl, and we define a direction of dt. It's in this case, it's a perpendicular component like this one. Yeah, and one can understand that the resultant b magnitude of this vector at this point of interest, it will be integral, where you will take into account contribution of all dl. Yeah, and if you will take this kind of substitution of variables, because in this case r and alpha, this is two variables, so you can express just leaving one variable, angle. Yeah, and in this case, you can calculate this integral, and it can be shown that B, it depends on cosine, it's an I, electric current. A, this is a distance, and alpha 1, this is this angle, and alpha 2, this one angle. Certainly, alpha 1 and alpha 2, if you have an infinite wire, they equal 0 and pi. So finally, if you have an infinite wire, you have this just a 1 minus 1, it's a 2i. This is for the infinite wire. So this is just an example how to use this principle, superposition principle for calculation. Another problem that usually is solved, and it's very nice to show analytically, well, it's a loop. It's a loop with electric current. So, well, we just have a wire shaped like in this case, but the principles are exactly the same. Well, we look on the dn, we look on the electric current, we plot position vector, we define dB, that is perpendicular, but in this case, one we can resolve in two. One is along axis x and one along axis b. So one can realize easily that because of the symmetry, we have a dn just in the opposite direction that will have the same minus and dB in this direction. So finally, if you will go around and you will integrate, you will have just this component along axis x, and this, like it's shown here, this is just L, and length of this loop, and we have a similar expression like we had. It's just a 2 pi. Pi times is higher as compared to the infinite wire. So B, well, you can see that in this case, well, it's a perpendicular to this surface, and B at this point can be calculated like this. It depends on the radius. It depends on the radius of this loop. Okay. Yeah. Magnetic field. Well, we know already that it can be produced by magnetic materials and electric current. And just that we have demonstrated how this electric current produces magnetic field and how it can be calculated using superposition principle. The one more case, how the magnetic field is produced, is by moving charges. If you have electric charges that have that are in directional motion, well, all of them they're moving in one direction. So one can find that, for example, this is a positive charge, like it moves in this direction. So how can I treat this moving charge? I mean, if I will look on this Biot-Savart law, so you remember it. IDL is important. IDL, yeah? So, well, I can consider, let's say, this motion of electric charge like some elementary current that is produced by this charge moving. Yeah, and this is a current density multiplied by ds. ds, this is area, elementary area where this moves. And it's multiplied by dl. This is the length that was covered during some time t. Oops. Hello. Hello, guys. Hello. How are you? Could you please speak a bit not so loudly? Okay, yeah. Maybe you will leave this exchange of ideas after the lecture, okay? Yeah, because I need to be concentrated. I feel some responsibility from here. So just don't introduce because to this process. Okay. Yeah. On the other hand, what is it? Current density. Current density I can express what we discussed already, like concentration of charges that were moving with the V, where V is the velocity, Q, that's elementary charge, and dV, this is elementary volume involved in these calculations. Yeah, and this one, n multiplied by dV, this is a number of particles moving with the velocity v. So this can be treated like some IDL. So, and finally, magnetic field by single charge will be equal dB. So this is, instead of IDL, I'm substituting this. And when I will divide, I will find that moving charge, it will produce magnetic field, and this magnetic field is a long cross product of V, like it's indicated here, and it indicates like 1 divided by R squared, because R I have in denominator and in the denominator. Okay, so I mean the expression are very similar. That this, instead of IDL, you have a V multiplied by R. Similarly, if I have a negative charge, so B will be of opposite direction. So in this case, it's in this direction. For the negative charge moving, B will be in the opposite direction. Good. Ampere's law. Well, in electrostatics, you remember, we had a superposition principle that allowed us to calculate electric field, yeah, and we had as well Gauss law that was like an alternative method allowing to us to calculate electric field as well, having some symmetry. Well, there is some correspondence as well with the magnetic phenomena. In this case, we should consider Ampere's law. What's it about? Well, let us consider with you that we have a conductor with electric current, and vector B is perpendicular, and you see nose, it's in your direction. Be careful. Yeah, and well, we know that if I have a electric current, then in this case, you remember, this is direction of current, and this is this direction of V. I am producing a magnetic field, and this is magnetic field. Lights are closing. Well, this is at some cross-section. Yeah. So, and I know already that according to the superposition principle, I should this BDL. Yeah. And now let us look on this and indicate this DL. It's like a elementary length here, and B, you see, can be shown here like tangential to this circle. Yeah. So this kind of integral B dl. So I'm going to this one point, ddl, to the next point, etc. And I'm adding this. It's called circulation of vector B. So if I will calculate this circulation of vector B, in this case that we know already, so what I will get, that B and dl, they are all, at every point they have the same direction. So cosine is equal to 1, and it's just equal to B. I know expression for B from this our analytical expression. You remember it was like 2I divided by R, I divided by R. So R, this is the radius or distance to the point. Yeah. And now if I will substitute here, I will get that this is just the integral of dl, but dl, this is 2 pi r. And finally, if I will substitute, I will get that this integral equals just mu 0 multiplied by I. Okay? Yeah. So this expression that, well, we wrote for this infinite wire with electric current, it tells us that circulation of vector B, it equals to the mu 0 I. And circulation, it means that you have a closed path. It's more general. You can apply for any configuration. It doesn't matter that we have chosen. This is just an example. We can have a configuration of our closed path like this one, and we can do the same, and we can have a more than one current. And if you will apply this, we will come finally to the Ampere's law that tells us that integral or circulation of vector around any closed path, like around this one, it's always equal to mu 0 multiplied by some I. So I have just a different electric currents, and they appear, let's say in this case it's a positive value, it would be negative, and this would be positive. So circulation or integral around this curved path, it equals to the electric current passing this area of integration multiplied by mu 0. This is Ampere's law. So this Ampere, you don't trust this. It's strange, yeah. Okay, just please, you will see as I will show you how to use it. Yeah, so it will be more easy to understand. Yeah, good. So now let us consider some configuration of conductors or electrical resistors with electric current. But along solenoid, well, how can we do this? Well, you just have a pencil and you're just winding the wire and you're already producing the device. And it's called solenoid. And if it's long as compared to the diameter, it's called long solenoid. What is specific about this? It's one can understand it if you will just think about this direction of B produced by. You remember while we discussed this current loop, we have many current loops. So as a result, we are producing very high density of magnetic field lines. Suddenly, these lines, they are close lines, you remember, like it's shown here, but the density of lines here is rather low as compared to the density that is concentrated within this. So, in this case, this device allows us to produce uniform magnetic field in some space, in some volume, Certainly it has a main application. This is another, and we will speak about this later. Yeah, and this is how should we use this Ampere's law to calculate. So it's very convenient. So, well, in this case, let us look on the solenoid. So one can see that electric current, it flows in this direction. So this is the end, and this is the nose of vector. And it appears all the time is every winding in the same direction. So all the loops, they contribute to this magnetic field like we spoke. And this is how we choose this closed area of integration. So now, if you will look on the direction of B, that is along this line, like was indicated. So, and outside, as a first approach, we can take that B is equal to 0 because of density. You remember, density of lines is rather small, and most contribution is done by this bar. In this case, dl is perpendicular to B, so it's a contribution, it's 0. And only this component appears important, and just calculating and resolving this 4 parts, we get just a single contribution by this part that is inside. In this case, B and dl are of the same direction. Just to think about the previous sketch I haven't demonstrated. Yeah, B is uniform, and I can put in front. And finally, dl, it gives you just the length of this surface you have decided to use in your calculation. It's if you will take the higher, you will put the higher value smaller than smaller. And on the other hand, according to the Ampere's law, the circulation of vector B along this closed surface, it equals to the number of currents. You see, they cross this area and multiplied by n, and every winding has the same current I. So finally, if I will equate these two parts, I will get that magnetic field inside equals electric current multiplied by n. This is n, it's a number of turns within this your chosen lens, and divided by L. But N divided by L, it's a number of windings per unit length. So you just can easily calculate this. The number of, you have a 1 centimeter and you count number of windings, and in this case you get very simple expression. B can be calculated in a very efficient way. Yeah. If you will, what happens if you will put some magnetic material inside? So if you will put some magnetic material, so in addition to mu0, you will have a mu in front. And you are able to increase a magnetic field in the, within the solenoid. Yeah, so we will see, as we will discuss about different application of these kinds. One more configuration, it's a toroid. To produce solenoid, we needed pencil. And for this, we need the donut. And we will wind, you know, the donut just very carefully around. More carefully, like it's shown here, because it's a long distance between the windings. But if you will wind this, so finally we will produce toroid. And you can calculate again magnetic field inside of the toroid using Ampere's law. For this, you just plot this extra this surface, and you count. So this is surface, and you count electric current that cross this surface. So one can understand that if you will choose this one, there is no any electric current, so magnetic field inside it equals to 0. There is no any electric current. If you will proceed like we did previously, BDL, so you will have something like this. That well, we have loops like this one, and DL, this is the integral. This is the radius. It's a variable radius. So you decided to calculate magnetic field at this point at the distance r. So and according to the Ampere's law, this kind of integral, circulation of vector B, it equals to the number of currents and I multiplied by mu0. If you will equate the right side, you will get finally B for the solenoid. For the solenoid, and you can see that the magnetic field inside, it depends on n, total number of n. If you will divide this by 2 pi I, you will get number per unit length. But just please pay attention. This R will be chosen we can choose higher or lower R, and in this case B is a different. B is higher here and lower at this part. Yeah, and this is again this device is used to produce confined magnetic field. Before it was in the solenoid, and now it's in toroid. And suddenly, as you will meet in the electrical engineering, so this is an inductor. It's widely used, and usually this instead of donut you can eat. But usually this ferromagnetic material is used, and in this case you are able to produce very high magnetic field, and it has a very high inductance. We will speak about this later. Okay? Good. And this is one of the applications. Certainly, this is a huge device. It's a tokamak. Well, who knows Russian? Well, I can tell you because this device originally it was constructed in Russia, and this is an acronym that comes toroidальная камера с магнитными катушками. It's a toroidal camera with the magnetic coils. Yeah, and this device it's used in plasma accelerators to confine plasma inside of big volume. And well, you can see this is some engineer stance to have a disintegration. You can think about the dimension of these coils. Yeah, so this is a device that is used for controlled nuclear fusion. So this is the future of our energy. We will, well, the people that ask for money, they promise that, okay, we will have artificial sun very soon, just to give us money. But let's say, but in near future, like 2030 or similarly, well, we will have a device that produces more energy than you apply to operate. And finally, we will have unlimited sources of energy. Good. Yeah, so one more thing. In electric field, you remember, we had a vector E and flux of vector E. So we just multiplied vector through some area, and we had a so-called Gauss law, as you may recall. I mean that the flux through the Gauss surface was equal to the charge that is inside of this supplementary surface. What about magnetic flux? Because this is a magnetic field is a vector value, like electric field. Yeah, and what is interesting? So the definition of magnetic flux it's the same like we did in the case of electric field. Well, we have a vector B, we have a normal, yeah, and this product B ds. It's elementary flux through the area S. Certainly, if we need to calculate through the closed surface, so we should calculate this kind of integral. This is a flux. Flux is measured in Wieders. So this is again scientist name. It's a Tesla multiplied by meter squared. Tesla Wieder. By the way, H, in what units magnetic field intensity is measured? H. Amperes per meter. Okay? So please recall. Tesla, amperes per meter, Weber. Good. Yeah, and what's the property of magnetic field lines? So probably you remember we said in the very beginning, magnetic field lines are closed. It means that if you have any closed surface, spherical surface, like we did, and you will calculate number of leaving lines and coming lines, they are equal. So finally, Gauss law for magnetic field tells us that BdS, flux of magnetic field through the closed surface, is equals to 0, because it's a solenoidal field. Magnetic field lines are closed. Number of lines entering equals to the number of leaving lines. Yeah, and I will just I didn't derive this, but in vector form, if you will apply, let's say, as a point, it would be shown that divergence of B, it's derivative versus space, it equals to 0. So this expression written in differential form means as following. So I'm sorry, I'm just skipping this. It's a bit long explanation, but let's say Gauss law in a very short form would be written in the following way as well. we will need this equation. If you will need, we can discuss a bit what is it gradient, what is it divergence, because in all the cases it's a three-dimensional derivative. Please read about this, okay? Good. So, for the Gauss law, this is dds is equal to 0. One more thing that you should learn. Well, we know that electric field, it acts on the charge. What about the magnetic field? Magnetic field, it acts on the electric current. So it means if you have a magnetic field and if you have a conductor with electric current, and we will put in the space, we will find that this wire will be acted by the force, and this, if I don't have this situation like this one, for example, this is our conductor, yeah, and this is a magnetic field, so it can be found that elementary force per unit length equals I dl, so this is a vector along this, cross product d, which means force is up in this case, and if you have a uniform magnetic field, if this kind of force that we can calculate, it's up, and it can be expressed like I, electric current, length V, and sine. This is the angle between two vectors, electric current direction and vector V. You can check this experimentally, this kind of expression. Well, you can produce, let's say, you have a north pole, south pole, and you have a direction of magnetic field. So this is a field between some ferromagnetic material in the gap. It's a magnetic field, lines are closed, you remember? Yeah, well, I have shown this kind of configuration in the very beginning. Yeah, so you can produce uniform magnetic field between these two surfaces. If you will put electric current inside, we will find that this conductor will move up, because the force, if you will change the direction, it will move in the opposite direction. So it's expelled by the magnetic field if you pass the electric current. So this principle is used in the loudspeakers, because in this case you have a wire with electric current. So this is the loop, and you put in the permanent magnet field. So you use the permanent magnetic material, and if you apply the electric current, these windings, they start to move depending on the electric current applied. So in this way, they move this membrane, and they oscillate with the frequency of electric signal. You can convert electric signal to the mechanical oscillation, and this is just, you have a very nice music. Yeah. What group is playing? What's your preferred group?
No particular group.
No particular.
No.
Okay. All music is good.
Yeah.
Good. Okay, so now you know how it works. One more thing. Well, we know already that a magnetic field, it acts on the conductor with electric current. But what happens if you have two electric currents? Well, actually this is nothing new. We can consider as following. One produces magnetic field, and the second is a conductor with electric current. And reverse. This produces magnetic field, and this is electric current. So we can calculate that magnetic field is separated by one conductor and by the second, and you can calculate the force, the forces, and you can define the direction, like we have demonstrated. So, for example, I will act on I prime and force will be down, and these forces are opposite, so I can apply just show the direction of force on this one, it will be up, so these two wires will attract each other. If you will change the direction, they will be repelled. It's the same like we had in electric current. And by the way, if you will use expression for B, and if you will calculate the force per unit length that acts on this, so we can show that this force, like it's shown here, it depends on the electric current between two wires, it depends on the distance, and this is the element. By the way, this expression that it's derived for two parallel currents is used to define electric current units, ampere. Ampere. You remember we said that ampere it's a coulombs per second. But as I said, the definition of ampere, it comes from the magnetic interaction. This is usually, according to this equation, if this interaction takes in vacuum, and the force per meter length between two conductors that are the distance 1 meter, is equal to 10 minus 7 newtons per meter, then it corresponds to the electric current equal to 1 ampere. 1 ampere. It means this is the definition of ampere. Just please try to remember this, where it comes from. Okay. This is a very important part in terms of application. Well, now we will put to the magnetic field not just the current, but we will put like a frame or coil in the magnetic field. So we have demonstrated already what happens when you have a magnetic moment. It means that in this case, if you will look on this part of elements, this is conducting this electric current, and this one, so you can easily find that if you have a configuration like it is shown here, this frame it's exposed to the torque. Frame rotates when you put a frame with electric current, so it tries to rotate to align. You remember, magnetic direction of magnetic moment should be in direction of B. But if you're changing the direction, so you can rotate this frame. So this is a principle of electrical motor. So just it's a converting electric current to the mechanical motion, And this is very easily. So rotation, it depends on PM and V. Now, well, you can understand that PM changes according to harmonic law, sine or cosine. So it means it will rotate with the frequency when the electric field, the electric current is changing. This is a very important part. Well, we know that moving charges, they produce magnetic field, you remember. But now, what happens if you have a magnetic charges moving in the magnetic field? Well, in this case, I can consider as following. So, for example, I have a moving the charges I can treat like a electric current density, like I have discussed, and if I put to the magnetic field, so magnetic field lines are perpendicular. We see the tail of the magnetic field vector. Yeah. So in this case, I know that force will be perpendicular to V and B to the vectors. Like in this case, it will be in this direction. Yeah, so now if you look on this evolving time of this motion, you will find that if it's at this point, it's F in this direction, it means that moving charge will change the direction, and finally you will get that positive charge will rotate in the magnetic field. So if you let the particle inside of the uniform magnetic field, it starts to rotate. and you see around magnetic field lines, yeah, and this force that acts on this particle, it's called Lorentz force. Actually, this Lorentz force, it has two components. In this case, we can have a magnetic field and electric field. So usually it's written as following. Just that we know what happens with the electric field, and this part is a force due to magnetic field. This is V cross product B. V cross product B. Good. So what is the mathematics of this? Yeah, Lorentz force, like we just discussed, it's an electrostatic force plus magnetic force that equals Q V. Well, let us consider that there is no electric field. It's just a magnetic field. So in this case, Lorentz force just has single component, magnetic component, and it's equals V cross product B, and the magnitude of this force we know already. It depends on dB and alpha. This is the angle in between two vectors, V and B. What kind of situation can we have? For example, Q moves in parallel to B, along B or opposite B. What is the idea? What happens in this case? Alpha is equal to 0. It means no force acts on the particle. So if the charged particle moves along B or in the opposite direction of B, Lorentz force equal to 0. It doesn't interact with the magnetic field. What happens if you let the particle on the right angle? Alpha, it's pi divided by 2. So you see, B is perpendicular, B is here, so it's 90 degrees. So in this case, force will have a maximum value. Force that yeah, and according to this equation, one can see that positive particles will rotate in one direction, and the negative particles will rotate in other direction. Anti-clockwise, clockwise. Yeah, and if you will try to calculate, let's say you can calculate the centripetal acceleration. In this case, it's a force divided by m. Force I know, QVB divided by m, and I will get. And on the other hand, centripetal acceleration is equals b squared divided by r. Well, r it's a radius of curvature plotted by the particle. So, and in this case, I can write the period of rotation is equals to pi I divided by b. And this is again 2 pi, and in this case b q divided by m. So the particle rotates with the period. With the period t, or it's 1 over t. It's called cyclotron frequency, and it depends on the charge to mass ratio. Some of you will be doing the laboratory work, and you will define ratio of electron charge to mass E to m. E to m. Actually, you need not just to measure the inclination or displacement in trajectory and no geometry, and you can define this. Yeah. And what happens if this angle is not equal to 90 degrees? So it means in this case, V has two components. One is a perpendicular, so it rotates, but it has as well parallel component. So if you combine, you'll have like a helical motion. The radius suddenly will be reduced by this sine alpha, like it's shown here. But in addition to this, you can calculate it during the period. During the period, it will reach the next point of this helical motion. Yeah, so this principles, motion of particles in magnetic field, are applied in devices that are dedicated to select to the spectroscopy application, and it's called velocity selector. Just let us realize that you have a flux of particles of different velocity. if this particle will move in this space, where you have a crossed magnetic and electric field, so they will be exposed to the electrostatic and a magnetic field. It can be easily calculated that particles that correspond to the principle when if V equals to EB, then in this case they move along with the trajectory, and they will be selected. Yeah. One more thing, I have mentioned it already. This is Thomson experiment that was used to define ratio of charge to M. So if you apply, let's say, electric and magnetic field, so you have this point on the oscilloscope, and if you just increase the magnetic field, you will get that it will be declined. So knowing V and knowing displacement, you can define E to M. E to M, this is actually what you need in your experiment. Mass spectrometer. This is extremely sensitive devices when you are measuring some concentration of elements with very low concentration, like a picomoles. It means 10 to the minus 12 moles or ppm or particles per mole. So in this case, they have this field. We have just discussed with you that if you have this, you are producing ions of the element you want to measure. Elements you want to detect, and you know the concentration of these elements. So there is this filter that was EB filter to perpendicular electric and magnetic fields, and just certain particles where magnetic force will be equal to electric force, and it gives you that the particle with the velocity equal E to V will pass on the this stripe geometry. So this particle will appear in this space. If I have different masses of the same velocity, so if they are moving in the uniform magnetic field, so they will move with a different radius, like it's shown here. And just putting here the detector, you can identify the different elements, and measuring, let's say, these currents due to the signs, you can identify concentration. Well, this principle is used in called very advanced surface analysis technique, like it's called secondary ion mass spectroscopy. This is extremely sensitive method, and it can be measured, it can be used to define composition. One more application, this is the Hall effect. Well, let us consider the situation that you have a conductive plate like this one, you have electric current, and you have a magnetic field perpendicular. Well, we know already that if you have negative charges, so they will move on the radius and they will be collected on this side. On this part, we will have just a reduced number of charges or positive charge. So finally, we will have an electric field produced by this collective, and you will have a stationary condition when number of electrons collected will be compensated by the electric field produced. So just measuring this voltage across, it can be shown that voltage appearing here, it depends on the electric current applied, B, concentration of the charges, E, and D, this is the thickness of this plate. So this Hall effect, so you will deal with the semiconductor devices. It's a very efficient way to measure concentration of the charges in the material. On the other hand, this kind of configuration is used as a magnetic field sensor. It can measure magnetic field. Just measuring voltage across this plate, like it's shown here. You can define magnetic field if you know the geometry and electric current applied. Yeah, this is one more application that if you apply plasma, well, we discussed a bit during last lecture. So if you have a flux of plasma produced, well, arc, for example, plasma in the magnetic field, and you will put the electrodes due to this magnetic component, positive and negative charges will be collected on these different electrodes. And in this case, you produce DC voltage. DC voltage that could be the next. It can be used already for electrical applications. This magnetic force, Lorentz or magnetic component of Lorentz force is a force that is responsible for operation of different type of accelerators. And this is one of the examples. It's a cyclotron. How it works? So let's say if you inject this at this point the charged particles, and you produce electric field here, so the particle starts to be accelerated. But if you put the magnetic field perpendicularly, so the particle moves along a circle, and it comes, like it's shown here, with high energy at different point. At this different point, it's accelerated, so the voltage that's applied here, and finally the particle moving, it's ejected here with the high energy, Yeah, so this is cyclotron here, and suddenly, if you will, there is a variety of different accelerators, but everywhere this magnetic force is, in many cases, magnetic force or magnetic component of Lorentz force is employed. If this is a variety. Well, there is some direct current voltage devices. This is just the free electrodes or electrodes with the increasing the potential, 1 megagraph accelerated, and for this one they need all magnetic field cyclotrons, just oscillating electric field. So the next, it's synchrocyclotrons. What is the idea of this? When the particles is accelerated, its mass is changing. It becomes heavy and heavy. And you should take into account this and to adjust the magnetic field to just to fit the right mass of the particle. So when you combine these two, so you can accelerate to very high energies. We will speak about this next semester. How the mass of particle depends on its energy. Yeah, and synchrotrons. So this is a very large ring accelerators, and one of the example, it's a Large Hadron Collider. So probably you heard that initiative of European scientists to join this stuff. It's a Center for Nuclear Research that's located in Geneva. And in this case, it's this synchrotron that is used in this collider. It has like a 27 kilometer circumference. It goes under the Earth, and it goes from Switzerland to France and back. And finally, you have a accelerated particle to very high energies, like a tera electron volts. It's a 10 to the 12 electron volts, and they're producing two beams, and they collide. And the people analyze the resultant particles that are produced. By the way, we are part of this initiative, and we contributed to the development of detectors, gaseous detectors that are used for ionized particles. And our university is a associate member of this. How it looks like, so this is inside, and this is particle are moving in this tube, and usually this you can go by a bicycle in the vicinity. We have visited this, it's really impressive. And this part, it's a part of the detectors, where all this area is filled with different detectors, and these kind of structures are located in different places, like it's shown here. Yeah. So that would be all, but we have some demonstrations if you like it, because we still have some time. Sorry, I was a bit fast, but as I say, I'm trying, to be in time, because some people came later, and I would like to repeat. During the last lecture, we will have a retake of the first quiz. The retake,
what is the first
the
quiz?
students only having the
Did you attend the exam?
grade below
How many was
5
you
are
scored
allowed to retake.
for the physics?
If you have 5,
4.
and you are
You
not
need to re-attend
satisfied,
that.
sorry, don't come.
The pass grade is
Because
5.
it's not possible. You should, if you really feel that this is that grade, go to the administration, get permission for the extra retake. Because I can't, I can't manage this process. I have just, the space to fill with the grade, and it's written over there. I can't change it. You understand, yeah? Situation. Good. So now, I will ask assistants.
Why is it only the programming teacher who is allowing retakes for school child?
I think it's only the physics that's not allowed.
Math didn't allow.
No math? No math. Math even raises the grade if it's even written in. No, the grade is written in it, and it can get up if you see that he did a problem or some shit you get it. So.
And he said, "Oh, we'll do this in the next semester." I'm like, half of us will be here next semester.
When do we get the 10 for the problem solving assessment?
After they've written their test. Next
We'll start from experiments. I told you it was not successful with electrostatics. Yeah. Oh, this is electric discharge. This is not the purpose to demonstrate. It's just a way to collect the charge. To collect the charge. And we have a positive charge and negative charge collected, and we will connect to the electrodes. Okay, so now, so now it's, well, we can touch it, but we will just,
So next week is the
these electrodes, so you can collect the charge here, and now we will apply this. Well, it's some serial small particles. Porridge reading. What's specific about this? That these particles they have a dipole moment. Remember, dipole moment. It means that they can be oriented in the electric field.
You got 3 for the...
You gonna sell?
Maybe you have some questions about the retake. The retake we will organize
The real and legit, right?
the class, and you will have 10 questions, short 10 questions. It will be a bit different situation when you have that in the class. It will be multiple choice. It will be just you need to write short answer in very concise way, like 5 minutes per question. This is what you are requesting.
Is that how it says?
If you write some formula, so just don't forget to explain all variables. If you want to explain something using the sketch, it's very welcome. And just to answer the direction of different vectors, etc., illustrate with the figures. Okay?
Is this the retake or the next exam?
It's a retake. It's a retake of the quiz. Retake. I mean, this is important for the people who failed in the first quiz. For the exam, you will have again the same situation like we had during the quiz, and you will have this multiple choice, etc. But it's difficult for me to arrange, this class, computer class. It's busy all the time, and we need to make during the extra time. So I'm proposing this case. Okay? Okay, yeah, so what you see, this is a space, and it's this is liquid, where the particle with the electric particle can be moved, and this is the electrode. Yeah. And we will connect to the electrode to the source of charge. So you see, if the charge is supplied, so these particles, they arrange, and we can see electric field lines. And you see electric field lines, they're perpendicular to the surface. So remember, this is a property of electric field lines. Good. So now we will have two electrodes. Just keeping the yeah, so we will have a positive charge and a negative charge. We will supply, we will produce like a electric dipole, and we will see what about the electric field lines in this case. Okay. Okay. Well, if you have two electrodes, so when we have some kind of field that's more or less uniform, but please pay attention. Everywhere, electric field lines, they are perpendicular, and in this case, they are going to the infinity. Yeah, and in this case, we have a uniform electric field between two electrodes. Okay. Okay. Yeah, so you see, this is the geometry of two electrodes. They have some curvature, and we have just in small area this uniform electric field everywhere. But now, if you will have a plate, parallel plates, so we are producing uniform electric field in big space, not only in this very small, but in this big space.
Hey, did you attend the seminar lab that day?
Yes.
3.
Two.
What was our difference?
This is one electrode.
I don't know.
Just to realize we're looking for
He didn't tell me about defense. He did not tell me about defense.
You just told that maybe this week. You need to complete the homework.
Yes.
You completed that.
The first one, I have to write it and upload it. The homework is done. You have to do this.
I mean, about
The bolt?
the previous one.
Oh yeah, the first one.
First process.
I did the first one, but did not upload it yet.
But team, I'm just telling you about that guy who just.
Yes. His homework. I did the first of his homework like that.
We don't need to upload.
We don't need to. You just give it in the copy.
No, at the defense time, we need to give that whole lab report, graphs.
And homework?
Yes, at that time.
Sure.
Completely different.
And we don't need to upload anything?
No. For
Sure.
that guy, we don't need to upload anything.
Did you understand anything during the lab?
Which lab?
His lab, like the first experiment and the second experiment.
something breaking.
Yes, breaking, then squishing.
Okay, so it's not very nice, not much charge was collected, but still you can see that the particles, they are trying to align in this space, and in this
How many
part,
laps
you
did you
see
complete at that
there is
day?
no alignment, so electric
Two.
field is concentrated.
How many do I have remaining?
Actually,
think
this
we
is
have
not
total
a
five.
nice picture
5 or
because
6.
of the low
Shit.
electric field. So the force that exposed this electric atom is rather too small. Not sufficient electric field to move.
Oh,
No, it's not aggressive. No. Okay. Okay. So now, probably remember this screening. What happens if you put some conductor inside of electric field? So electric field lines, they are perpendicular everywhere, and there is no electric field inside. So let us check this. Okay, well, you can see that these particles, they are arranged according to the electric field lines that are perpendicular to the surface. But in this part, you see, there is no, it's irregular structure completely. So they are not acted by this electric field that you are producing. So this is a very efficient screening. So you can be inside and you will not be acted by this electric field. Okay, that's good. Okay, well, you saw the electric discharge that happens, it's a spark. Discharge. It's not an electric field. The streamers appear, and we produced lightning artificially. Well, it's something like between these two electrodes, just more charge was was acting in this charge. Yeah, and so now we will have some magnetic phenomena. One of this, it's well, this is a tube that you will remove the air. We will pump it. We have this mechanical pump, and
what is happening?
well, you see it.
Oh, yeah, I see.
It was a distance d and pressure p. D is important parameter that defines when this discharge starts. Yeah, so it means that just reducing pressure to this huge distance between the electrodes, we can start this low discharge. Okay? Now, this low discharge, it depends on the gas that we are using during the experiment. So you saw that different gases, they glow with a different color, and suddenly the intensity. Okay, well, So dependence on the pressure, you can have a uniform distribution, or you can have this kind of chopped discharge. Yeah. So the next. Okay. Okay, it's just a please show the is it gun set up? Yeah. Well, and now this tubes are filled with different gases, like I was demonstrating to you.
The second one, he's shivering.
Okay.
His hands are shivering.
What second?
When he touches the second one, at that time his hands are shivering.
And different pressure, Okay. Okay. Yeah. So sorry. Yes, it's a different pressure.
So the experiment failed.
He's finished. That's what the bolt type. When we touched down there, I'll show you a video.
You're still carrying the phone around. Probably not open to it.
Cash in the
It looks nice. So it's,
would you like to
demonstration how this
do this? We just go to the
approaching, I just to change the potential of this capacitor. It's remember, it's what we discussed sensors, how this acts. Yeah, so I'm this like some kind of capacitor. Yeah. This we have a high frequency electric field in the vicinity. This gas of this tube can be excited as well by this strong electric field. And in this case, well, I'm changing the distribution of the charge due to extra capacitance connected to this. Yeah, and this is just the different gases in the tube, and you can see capacitive coupled system when it's excited with different gases and they flow through.
അവിടുത്തെ ഇലീഷ്യ മ്യൂസിയം അവിടെ ഉണ്ട് ഇത് പോയി നമുക്ക് പിടിക്കാം ഞാൻ പോയില്ല
കാണിക്കണം അതിൽ കാണിക്കാം കാണിക്കാം
സെയിം തിങ്
Yeah, so that's all for today. And as I say, the next time I will try to complete. It's a really big amount, but maybe I will need YouTube or read something. Okay? Well, if you have any questions, everyone has to come to me to talk and discuss and sign.